In this video, we're going to do a couple more examples of double and iterated integrals. In particular, we're going to focus on ones that have geometric applications. Right? So for example, for our first example, let's say we wanted to find the volume of a tetrahedron bounded by the three coordinate planes and the plane 2x plus 3y plus z equals 6. All right, so in order to answer this question, what we're going to want to do is find the volume under this, under the plane that we're given, the 2x plus 3y plus z equals 6. So we're going to want to use that as our function that we're going to integrate. And so we can solve that plane for z, and that'll be our f of xy. So our function in this case will just be our z, which will be 6 minus 2x minus 3y. All right, so this will be the function that we're going to integrate. The next goal is to find the region that we're going to be integrating over. And so in order to do that, we could look at where this plane intersects the coordinate planes. The coordinate axes. So the x-axis, y-axis, and z-axis. And so in order to do that, if we want to find, for example, where it intersects the x-axis, we're going to let y and z both equal to 0. And so if we do that, we get 6 minus 2x equals 0, and we get x is 3. So it'll intersect the x-axis at 3. Similarly, it'll intersect the y-axis if we let x and z be 0, and we get y is 2. And the z-axis, it'll intersect when x and y is equal to 0, or are equal to 0, and so we get 0, 0, 6. And so we can come up with a rough sketch of our three-dimensional situation as follows. Okay, we're going to find the points 3, 0, 0 on the x-axis, 0, 2, 0 on the y-axis, and 0, 0, 0, 0, 0, 6 on the z-axis. Right? And we know our tetrahedron is bounded by those 3 points. And so our plane intersects here. And so we have this particular plane that I have in red. And so if you bound this along with the 3 coordinate planes, you can see our tetrahedron right here. And so what we really need to do for the limits of integration, we need to determine the region in the xy plane. So I'll remind you that this is x and this is y. And so when we go to draw the region, the region is a triangle. It hits the point 3, 0 on the x-axis, and it hits the point 0, 2 on the y-axis. And so our region is this triangle here. And this is our region of integration. And so this is the region that we need to describe. We have 2 different options for which iterated integral to use. But we notice that one of the boundaries of this region that we use in our iterated integral is going to be the hypotenuse of this triangle. And so it's more natural to write this hypotenuse as a function of y in terms of x. In fact, it's very easy to do. We see that it is a line. We see that it has a slope of negative 2/3. And we see that it has a y-intercept of 2. So I can simply write down that this is y equals negative 2/3 x plus 2. And that tells us that I want y, at least in the easiest possible case, I'd want y to range between functions of x, which means I want x to range between 2 constants. And so the x values of the region here range from 0 up to 3, right? The largest value of x in this graph in this region is 3. And then y is going to range between 0 and this line, negative 2/3 x plus 2. Right? And so we have our function f of x, y that we're going to integrate, and we have our limits of integration from our region in the plane. And now all we need to do is compute the iterated integral. All right, so our volume, which I'm going to call capital V, right? If we use a double integral, it's going to be the integral from 0 to 3 of the integral of 0 to negative 3/2 x plus 2 of the function 6 minus 2x minus 3y. Right? And this will be dy dx. Right, so this was all determined on the previous slide. We had our limits of integration. We solved for our function f. And now we just have to compute this iterated integral. Right, so we're first going to anti-differentiate with respect to y. So this would be 6y minus 2xy minus 3/2 y squared. And we're going to evaluate this from 0 up to negative 3/2 x plus 2. All right, so when we evaluate it, we get 6 times, and I'm going to go ahead and start writing this as 2 minus 3/2 x. I'm not sure why I haven't been doing that, but I'm going to now. So 6 times 2 minus 3/2 x minus 2x times 2 minus 3/2 x minus 3/2 2 minus 3/2 x squared. And now when we substitute in 0, we can see that every term has a y, so we get a 0 there. And so this is our integral. So again, I'm going to go ahead for purposes of time and space. I'm going to go ahead and leave the simplification of this to you. But if you work through this, what you should get is the integral 0 to 3 of 2/3 x squared minus 4x plus 6. Right? And now we just differentiate with respect to x. So this will be 2/9 x cubed minus 2x squared plus 6x, evaluated from 0 to 3. And so when we evaluate at 3, we get 6 minus 18 plus 18. And then evaluating at 0 is just subtracting 0 from that. Everything is 0. And so this ends up being 6. And so the volume of this tetrahedron is equal to 6. So let's look at another example involving geometry. In this one, let's compute the area of a region in the plane. So let's say we wanted to find the area between two curves. So let's find the area between 3x squared and y equals 2 plus x squared. Now you should be immediately screaming in the fact that we do not need multivariable calculus to do this. In fact, one of the first things that you learn how to do when you learn how to integrate in single variable calculus is you learn how to find the area between two curves in the plane. And so this is something I would expect almost every Calc 1 student to be able to do, particularly with these functions being very, very simple functions. And so really what we're going to do here is we are going to compute this using a double integral. But we're going to do this to see sort of how we would compute an area with a tool that typically computes volume. We're going to need this shortly when we turn our attention to polar coordinates, and we're going to want to use double integrals to compute integrals of regions in polar coordinates, and it's going to be the same procedure, but we have to sort of understand how to use a tool for geometry or for volume to use that tool to be able to compute areas. And so the basic idea is very, very simple. If I want to compute an area and I want to somehow turn that area into a volume without changing the numerical value, of course it'll change the units from square units to cubic units. But if I want to change an area to a volume, what we could do is just take that region and form a solid by making at every point in our region a height of 1. And then the volume would simply be the cross-sectional area, which is the number that we want, multiplied by 1. And anytime we multiply a number by 1, we get that same number back. And so what we're going to do in order to get this area with a double integral is we're going to integrate the function f of xy equal to 1 on the region between the curves. Right? And so this way, what we're actually computing is a volume, but we know because the height of our solid is 1, we know the numerical value of the volume is going to equal the numerical value of the area. Right? And so in this case, we've actually already dealt with these two curves in a previous example, so we'll be able to get some of the basics out of the way. We know that this curve lies between x equals -1 and x equals 1. You could just set the curves equal to each other and solve to find that. And we know that y is going to lie between 3x squared and 2 plus x squared. And we want to integrate that function 1, right? dy dx. Right? And so this is a relatively straightforward integral to do. So we have the integral -1 to 1 of y, evaluated from 3x squared to 2 plus x squared dx. And that will give us 2 plus x squared minus 3x squared and so we have the integral -1 to 1 of 2 minus 2x squared so we have 2x minus 2/3 x cubed evaluated from -1 to 1. Right, and so we get 2 minus 2/3 minus the quantity -2 plus 2/3. And this will equal 8/3. Right? And so this would be the area between these two curves. Right? Now, along the way here, you might have noticed we ended up, after the first iteration of the integral, we ended up with this. And this is exactly the formula you would have used in Calculus 1 to find this area. You know the curves intersect from -1 to 1. And of course, now that I write this, I see that I wrote dy there. I actually meant dx. I wrote dx everywhere else. I'm not sure why I wrote dy there. But this is the exact integral that you would use. You would have x going from -1 to 1, because that's where the two curves intersect. And you would have the upper curve, 2 plus x squared, and you'd subtract the lower curve, 3x squared, and then you'd integrate that. And so, we're not doing anything different here, other than we're computing really a three-dimensional quantity, which is the same numerically as the two-dimensional one. But like I said, if I were just asked this question, I would probably not do this. I'd probably just use the single variable approach. However, when we get to polar coordinates, if you've seen areas in polar coordinates before, there's a formula that you have to remember for how to compute the area of a region inside a polar curve or between polar curves. And it's not as nice of a function. It's not as nice of a region or of a process as this is. And so when we do that shortly, we can extend this idea of integrating the function 1 over that region, and then therefore have to not remember any kind of formula. And it's a lot more effective to do that.